Okay, now we're recording. Okay, starting with 14. A baseball pitcher throws the ball into motion where there's a rotation of the forearm about the elbow joint as well as other movements. That makes sense. If the linear velocity of the ball relative to the elbow joint is 20 meters per second at a distance of 0.48 meters from the joint, and the moment of inertia of the forearm is 0.5, was the rotational kinetic energy of the forearm. Okay, so yeah, this one's a little funky. Remember, rotational kinetic energy is this. So Ke and ROT is a subscript, is 1/2 I omega squared. Now, we're not given the angular velocity. We are given the inertia, so that's good. For the angular velocity, remember, it's going to be, actually, I always get this mixed up. It's going to be V omega times R 1. And just to double check, because there are a lot of formulas, all you have to just go to your resources. They're all in Schoology, even the solutions too. But if I were to do this, there you go, right? V equals R omega. So we got it. So omega will then be your velocity divided by your radius. We have the velocity and we have the radius. So there you go. And you're squaring that. So you can do 1/2 times 0.5, that's your I. Your omega is V over R, or in this case, 20 over 0.48. And then square it, of course. And just work it out. That's all you're gonna do. Easy peasy. Square it, then actually we divide by 4 because times it by 1/2 twice, and you get 434. So I got something like that, you know, because you do have to realize to use this formula. And we make a multiple choice, and that probably might be worth 4 points. I like that problem. That looks like a good one. Now I'll start with 10. What's going on at 10? So we have a motorcycle wheel, okay. You have the mass of it. It's a ring, inner radius of 0.28. Outer radius of that, okay. Motorcycle is on its center stand, so the wheel can spin freely, fine. If the giant chain exerts a force of 2200 newtons at that kind of radius, what is the angular acceleration? Okay. So again, we have formulas to help us out. So remember, you could say tau, or torque, is your force times radius. We know this, right? Also, tau is I times alpha. We know that as well. So we can send them equal to each other. F times R is I times alpha. So I think that's probably where some of you guys might be getting stuck, just realizing you need to do that. So I know my force. Radius, I'll switch that to meters, so it'll be 0.05 meters. Alpha, obviously, I want to solve. And I do need to know what I is. I is going to take a little work. And you have to read it very carefully. They say it's an annular ring. And they have an inner radius and an outer radius. So I'm guessing I have to use both. Or maybe not, I don't know. Let's see. So we could probably use the hoop. And the axis is right here. So you can kind of think of the axis kind of going that way. And I'm just a little confused about the inner and outer radius. Yeah, a little bit confused about that one, but oh, actually, I do see a formula for that. Okay, looks like I got cut off. Maybe that's why you're stuck. But let's look at the notes again. So 4, 5. Yeah, yikes. It looks like I got cut off. It's right here, actually. It's m over 2, and you have to add the square of the 2 radii. Sorry about that. So that's the ring. That's like an annual ring. M over 2, R1 squared plus R2 squared. I'll give it to you. I'm not going to, I'll just say, hey, I is this, hence, don't worry about that. But yes, that's what we have to use. So we have to use M over 2. And then R1 squared plus R2 squared. Well, you know your M, 12 kilograms, so that's easy. The radii, 0.28 squared plus 0.33 squared. Work it all out. And bring it back in. So your force is 2,200 times 0.05 equals I, which is 1.1238 times alpha. And we should get, okay, I got a ridiculously big value. So I don't know what I did wrong. Hold on a sec here. 12 kilograms divided by 2.28, 200. Oh, okay. I just can't use a calculator. Hold on. 200 times 0.05 divided by 1.1238. No, we're cool. Maximum was divided by 0.05. That was stupid. So you get 97.9 rads per second squared. So we're good there. The tangential acceleration, there's a formula for that. And again, a lot of formulas going on here. So I was trying to just try to get all your formulas in order. Just right here. So that's all that's happening. Maybe you guys could work on that tonight and tomorrow. We could kind of go through the formulas, make sure you guys have all the formulas you need. For R alpha, you'll just keep the 4 notes open. So that's easy. You already know your R, 0.05. Your alpha, 97.9. That doesn't make too much sense. On the outer edge of the tire. Oh. Wait, hold on a sec. I guess you have to use a different R value. I was thinking of the drive chain. I think it's on the outer edge of the tire, so I have to use that 0.33. So my bad. Let's try that again. Yeah, we're okay now. 32.2. Yeah, so you're using 0.33 times 97.9, so you get 32.3. And it's meters per second squared, by the way. So that's a little bit off there. Okay. Then, how long from rest does it take to reach an angular velocity of that? And remember, that's one of our kinematic formulas. going from rest at 0. You want 80. Your alpha is 97.9. You solve for t. That's it. You get about 0.817. So hopefully that makes sense. I think that could be a good problem that I can put on a test as well. I like 10 a lot. But I'll tell you what the inertia equation is. Don't worry about that. I'll tell you that to you. Maybe that's where you're stuck. I don't know. Also, it's just unfortunate that it was kind of, I don't know why that was blocked. Whoever made this file probably wasn't careful there. So, okay. Actually, come to think of it, I do have the word. No, I think I got rid of all the word docs. That's right. Okay, clear. Let's move on to 1315, and then we'll move on to the other packet. 13. Calculate the rotational kinetic energy. Okay, again, we know this. And we're using the same inertia as before. Our inertia was 1.1238. So remember, so yeah, if you had a hard time with 10, then of course you wouldn't be able to do 13. And that was roughly 1.1238. Yeah. And that's gonna be a kilogram times meter squared. Those are the typical units for that. And yeah, 1/2 I omega squared. The omega you already got is 120. Just work it out. So we're going to scroll down here. Okay, it's just a lot of them scroll down. 1.1238 times 0.5 times 120 squared. Yeah, you end up getting 8,091.36. That's joules, or 8.09. Final 15. While playing football, a kicker rotates his leg about the hip joint. No inertia, boom, that makes it easy. Rotational, there we go. Angular velocity, easy peasy. So 175 equals 1/2 times I times omega squared. Your I is 3.75, work it out. You solve for your omega. If you get it correctly, 175 times 2 divided by 3.75, root the sucker, you get 9.66. What is the velocity? So remember, omega times r equals v. So now you know the that's pretty much a radius to 1.05. So you see 9.66 times 1.05. So again, these are very, very simple calculations. You should get 10.14 meters per second. And then last explain how the football can be given a velocity greater than the tip of the shoe. I'm not sure what they mean by that. Let's not worry about it. Okay. So hopefully you guys are cool with that. That kind of closes the book on this section. Any questions? Okay, no? Okay, great. Questions? No? Right. Let me close that down. Actually, I'll keep it open because I might want the, well, let me actually open up the solution key because I may need to form those. Okay, rotational motion practice test. So I found this online. It looked really good. I thought there were some really just outstanding questions here, and of course the answers are included. Any of these that you like to ask? Some, and just, some might be a little bit wonky. Again, all the answers are here. Not worked out solutions, obviously. So any questions from this that if you looked at last night, or if you're looking at now, you're like, okay, I'm not sure how to do this. Let me know. Anything right now you'd like me to work through? Okay, well, I'll go through page 1. Just kind of talk about you guys. And then I'll have you guys go in breakout rooms and kind of just discuss maybe the next 2 pages and see if you guys have questions on that. Okay, so we'll start with number 1. What's happening here? A spinning ice skater on extremely smooth ice is able to control the rate at which she rotates by pulling in her arms. Okay. Which one statements are true about the skater during this process? And it could be more than one correct choice. Okay. Now, remember, she's going to spin faster, just so you know, when she pulls her arms in. And the reason why that's happening is because if we consider her inertia, so your inertia, like if you're kind of like this, you have your body as a cylinder, and you have these 2 little extra cylinders coming out of your body, like your arms. And then when you bring them in, that changes your inertia. And remember, we had a discussion about angular momentum, which is I times omega. So when the I changes, the omega changes. And because the inertia actually will be reduced when you bring your arms in, there's kind of less like resistance. So you're gonna move faster. So you're gonna experience a much faster, actually let me open that again. Put it right next to here. Let me just adjust that just a tad. Yeah, anyway. So coming back to this packet. So her kinetic energy will change because her omega is changing. Momenters, no, that changes, that drops. And kinetic energy actually is going to increase. She's subject to a constant. The torque, yeah, obviously will change because we know torque to be I alpha, but it won't be constant necessarily. So we know it's not 0. It's going to be A. You're conserving the angular momentum. And we have a chat here. Okay, no problem. Okay, so let's look at 2. The moment inertia of solid cylinder ballast acts given by the following equation. If cylinder rolls without slipping, the ratio of the rotational kinetic energy to its translational kinetic energy. Okay, now remember, translational kinetic energy is 1/2 mv squared. You know this, right? So here's what we do. I can put a problem like this too, and this could be a little tricky. 1/2 I omega squared is this. This here is 1/2 mv squared. Now remember, v is omega times r. So we can actually do a substitution. And I, remember, is 1/2 mr squared. So 1/2, and I is, you can have another 1/2 m r squared omega squared. And of course, if I distribute this, I get 1/2 m omega squared r squared. So these are virtually identical. The only difference is the rotational kinetic energy is multiplied by 1/4. So you have 1/4 m omega squared r squared, 1/2 m omega squared r squared. So it's a 1/4 to 1/2 ratio, or 2 to 4, or 1 to 2. So that's why it's going to be B, that one. So this is kind of key. If you don't recognize that, then yeah, you're going to be lost to this problem. So you got to do a substitution for the linear velocity and change that to something that involves angular velocity. Then you can compare rotational kinetic energies, and translational kinetic energies more easily. So that's B, number 2. We keep moving. 3. If a constant net torque is applied to an object, that object will, remember torque equals I times alpha. So of course, if this is constant, then we kind of expect these other two things to be constant as well. And inertia kind of is, you're kind of stuck with that. Like it's not really going to change. Like whatever object you're dealing with, that's going to be its inertia, right? Because inertia is, something with mr squared. Maybe sometimes you multiply by half. It could be a lot of different things, but whatever the object is, that's just going to stay the way it is. So that's going to be constant as well. So of course you expect alpha or angular acceleration to be constant. Inertia is not changing. No, you don't have a constant angular velocity because then you have 0 net torque. If that's true, then your net torque is 0 because you have 0 angular acceleration. And then, no, A is out also. So that's why T. So these are all great questions. 4, a disk, a hoop, solid sphere are released at the same time. They are all uniform and roll without slipping. In what order do they reach the bottom? Okay, so we actually had this something kind of like this yesterday. Let me actually show you the solution here. So this, these problem sets are actually your best friend. You really want to have these out. So we worked through that. Actually, was it 4-5 we did that? Yeah, we did 4-5, my bad. And we looked at conservation of energy. And we saw that the solid sphere had a faster velocity than the thin sphere. And that's mainly because the solid sphere actually had a lower inertia. Remember, inertia is like resisting your motion, right? You can think of it this way, like a really big dude is probably not gonna run as fast as someone who's super skinny. I mean, like if you looked at, I don't know, an offensive lineman compared to an NFL wide receiver, wide receiver is probably gonna run pretty faster, right? Because he doesn't have as much mass. That kind of makes sense. So anyway, the less inertia you have, the faster you're gonna be. Solid spheres, I see here, don't have as much inertia as thin spheres do. So that's just kind of just the basis of the equation to see. So going back over here again, a disk, a hoop, and a solid sphere. So a disk is like a cylinder, which is 1/2 mr squared. Well, 1/2 is greater than 2/5. I know this. And then they said a hoop. Hoop is mr squared over 2 as well. Actually, but my guess is we're probably rotating it like this. They probably should have been a little more clear. Yeah, my guess is probably rotating that fashion. Not like you're not doing the hoop kind of like this. It's kind of like going like that. Not like, I don't know if I have anything circular. Okay, got a bulb. This is a hoop. Anyway, it's rolling like this, right? Not like that. That makes sense. Nice bulb. Granola everywhere. Awesome. Anyway, so hoop has the highest inertia. That's gonna be the slowest. That's gonna be second, and that will be fastest. So they want us to go in order. Which order do they reach the bottom? The sphere is gonna hit the bottom first, then the disk, then the hoop. That's why it's C. So again, the sphere had a lower inertia, so it's gonna get there faster. So it reaches the bottom first, then second and third. I mean, you could go through the actual work if you wanted to, but it's just a very labor intensive. So I think we just generalize, right? That's what we notice for this. So that's kind of takeaway there. We'll look at 5, 6, 7, then I'll break guys into groups to do the next 2 pages. Or at least discuss them in your groups. 2 equal magnitude forces are applied to a door at the doorknob. Okay. The first force applied perpendicular to the door, second is applied at 30 degrees. Well, remember, torque is not just F times R, it's F times R times sine theta. And theta, is 90, if it's 90 degrees, you're doing sine 90 degrees, which is 1. So doing it perpendicular is actually going to get you the most torque that you can get. 30 degrees is not as much. So it's definitely going to be the first force, so that's why I'd say. 6. The angular momentum is that in 2 seconds. What magnitude average torque acted on the object? So remember, we do have some formulas here that involve time as well. And angular momentum is also the same thing as tau times delta t, just like we had impulse equal to F times delta t. So the other momentum is just going to be torque times time. That's all. So easy. 10 equals torque times 2. Your torque is 5. That's all. So we get A again. 7. Suppose a solid uniform sphere of mass m and radius r rolls without slipping down an inclined plane starting from rest. The angular velocity of the sphere at the bottom of the incline depends on. Okay, well, remember, we're using conservation of energy here. And so kinetic energy is going to be 1/2 times I times omega squared. But here's the thing, though. I, we know, is going to involve 1/2 mr squared. So mass is involved, for sure. So if you're tempted to say C, because you see mass and radius, yeah, you could be fine. Mass actually won't matter. Here's the reason why. So conservation of energy, right? Potential energy, you know, is mgh. So you're on a ramp, right? Or inclined plane. You have a sphere. And it's rolling down, right? And of course you have a height. But initially there's no kinetic energy, right? Initially you have 0 kinetic energy. Finally you have a bunch of kinetic energy. When you look at the conservation of energy here, and by the way, your kinetic energy is also going to involve 1/2 mv squared as well. And we know that V is omega r. So what's going to happen is that you're going to set, when you work this out, you're going to have mgh on the left side. On the right side, you're going to have 1/2 times your inertia, which is 1/2 mr squared times omega squared, plus 1/2 velocity squared. And you can convert the velocity to omega r. The thing is that the masses are going to cancel, because you can factor out the mass from the right side of the equation and cancel out the mass on the left side of the equation. So it won't matter. Of course, the height will impact, but they didn't have it as an option. But definitely the radius impacts it too. So yeah, so mass won't matter. Mass actually cancels out. So if I do give you a problem in a test where I'm maybe asking, hey, find me the velocity at the bottom of the hill or bottom of the ramp, whatever, and I don't give you mass, don't worry. Don't worry, because it's going to cancel out if you set the potential energy equation correctly. If I actually show you again, mgh equals, you know, because the rest of the kinetic energy is 0 before you roll it. Then when you roll it, there's no potential energy, it's all kinetic. So you have 1/2 times 1/2 times mr squared omega squared plus 1/2 mv squared. Guess what? The m can cancel out. We have 1/4 r squared omega squared plus 1/2 v squared of mgh. The m's cancel. So you don't need mass, won't matter. So you want to be mindful about, and I could ask that too. I've asked those like select all that apply. I like that question a lot. So, you know, our tests could just be, I could just repeat these questions just so you know. So make sure you watch this video and are paying attention. Okay. So I'm going to clear my drum. I've been talking for the last 35 minutes or so. So now it's time for you guys to work in groups. So I want you guys to work through 8 through 21. Now, if you've already done these, then just talk about it with your group and just go through and make sure you guys understand what's going on or help each other out. When we come back, we'll kind of do some of the other ones together. And this will be perfect because then we could do circuits when we get back from lunch break. I'll give you guys about 20 minutes. If you guys want to get ahead, by the way, feel free to do so. That's no problem at all if you feel so inclined to get ahead. So I say do pages 2 and 3. If you have time, look at page 4 as well. So 8 to 21, but if you can get up to 26, that's fine too. And we'll see if you have any questions when we get back from the breakout rooms. So let me stop sharing. We got 12 people, that's great. We're gonna do 4 groups. Create the rooms, and we'll set this for 20 minutes. Okay, you guys can go.
I want you to pay it all, and we finish the contract. Since you don't pay it yet, I checked my account. It is 26,678.